All right, we'll get started. Thank you for joining. Now, if you can hear me, all right, I want you to signal a yes in the chat window. Okay, pretty good. Good. There's an option to actually the green tick mark, look for the button that says vote yes. Okay, so I received quite a few yes. So that's good. We'll get started. Hope you're safe through the coronavirus situation. A couple of quick important points about the upcoming midterm. On Thursday, it will be during the class time. It will be on Canvas. Okay, it will be available on Canvas. I made the midterms. I created the midterms. They're available on Canvas now. They will open up just 5 minutes before the class time. Okay, a couple of quick suggestions. You want to join in the Zoom session at least 10 minutes early. It will be a different link. I will be sending you a different link. So the class link will not be active. The exam midterm link will be different. The Zoom meeting will be different. I strongly suggest you at least join 10 minutes early. Now, a webcam and a mic are required. Before I let you into the meeting, I'll put you in a waiting queue and then verify your webcam and microphone and make sure they're functional, and then let you in. Once you are in, that is when you will have access to, you'll have the access code to take the exam. Okay, so calculator is optional. I don't think there are any problems that need you to use your calculator, but it's okay to have one if you feel you need it. Okay, I also posted previous midterm on Canvas. Okay, what is different about this time is that there are 50 questions. The previous midterm had only about 33 to 34 questions, but this semester's midterm has a few more questions, 50 questions. Okay, in some respects, it is very similar to the previous quizzes, and in some respects, it is different. So if you look at the previous quizzes and the midterm and use that as a starting point for your preparation, that would be good. Don't end your preparation with the quizzes and midterm. They should be just your beginning points. Okay, understand the questions and the logic behind these questions. Okay, now once you are admitted into the meeting, okay, after verifying your microphone and webcam are functional, your access code will be given to you in the Zoom meeting. Okay, once you have your access code, you should be able to begin your exam. Okay, so that's the idea. Any questions, please? Questions, comments, concerns? No cheat sheet like I mentioned in the announcement, Canvas announcement. I will provide you the equations or constants or any variables that you need to take into account. Okay, so I'll give you some general useful equations. Okay, let's see. Is there a volunteer who can keep track of? Is it all multiple choice? I see there's a question from Brandon in the chat saying, is it all multiple choice? Most of them are multiple choice. Some of them are fill in the blank, true and false, that kind of questions that can be automatically graded. Okay, now Brandon, can you keep an eye on the chat window and make sure to alert me if somebody chats? Okay, Brandon says yes. Yeah, you may have to. The question is, the previous questions, previous quizzes. See if you can email the TA and see if he can take a picture of your quiz and give it back. But even if not, I have made the previous quizzes available on Canvas, and I have made these solutions available on Canvas. Okay, so in addition to that, my Google Notes actually has the solutions to this semester quizzes as well. So if you go to Google Drive and if you go to Google Drive and look at the documents posted there, that should have the solutions to the this semester quizzes. Okay. All right, let's begin by looking at what we did in the last class. Okay.
Quick question. I wanted to know if you would provide us the equation sheet early.
The equation sheet early, it's not a sheet, actually. It's going to be embedded into the instructions of the quiz, of the exam. So I'm still putting that together. Okay. Another question is from Wesley, is the exam going to be, do we have to scan? You don't have to scan the exam. It's all fully online. Okay, so I'm afraid I may not be able to provide you the equation sheet early. It will be embedded into the exam frame. Okay. All right, any other questions, please? Okay, now Brandon is going to keep an eye on the chat window so I can concentrate on my screen. Now, we started looking at power in the last class. Okay, I mentioned that the power in isolation or energy or delay in isolation by themselves are two not so good factors to optimize. Instead, what we want to do is optimize the power delay product or the energy consumption product factor. That way, we are not optimizing one at the expense of the other. Okay, and I also mentioned we quickly looked at the power consumption issues. In CMOS, the power consumption is usually in two different paradigms: the dynamic switching, that is when most of the useful work is being done, and also static power consumption, which mostly comes from leakages. Okay, that's what we looked at. We looked at the fundamental equations for power, energy, and average power. Okay, and then I showed you how energy is stored in a capacitor, how energy is drawn from the power supply during the full cycle of charging and discharging. Okay, during the charging phase, energy is drawn from the power supply. During the discharging phase, it is dumped to ground, and charging happens through the PMOS transistor, and discharging happens through the NMOS transistor. Okay, that's what we discussed. I talked about the short circuit current and then the current and the voltage curves in relation to power. Okay, and I gave you an expression for switching power. Remember, switching power is part of the dynamic power. Okay, power switching is a function of the capacitance, the voltage squared, and the switching frequency. Okay, if I want to express the switching frequency in terms of the master clock, so this switching frequency can be expressed in terms of the master clock, this guy. Okay, F clock, in terms of the activity factor alpha. Okay, I discussed that. In addition to that, I talked about the short circuit current, which is a blip of current in CMOS when both PMOS and NMOS transistors are momentarily on for a very, very short duration of time. Okay. So these are the different power dissipation sources. The dynamic power and the static power constitute the total power. The dynamic power itself has the switching power, okay, and the short circuit power consumption. The static power itself is the sum of all the leakages. Okay, and then we went into an example of dynamic power estimation, and then we saw that a large number of memory transistors with a really small activity factor, they consume almost the same amount of comparable amount of power to a small number of logic transistors that are switching really fast, okay, that have order of magnitude higher activity factor. Okay, and then we went into the idea of contention current. Did I talk about contention current in this section?
I don't believe we did.
Okay, okay. The idea is contention current happens in logic that's different from CMOS. Okay, in CMOS logic, there is no contention current. Okay, in CMOS current, there is no contention current. CMOS, where the PMOS transistor is off, then the NMOS transistor is on, and vice versa. There is a complementary action in CMOS logic. Okay, but if we look at different logic families besides CMOS, so if I look at this guy, okay, called a pseudo NMOS logic, okay, what you can see is the pull-up network is composed of just one PMOS transistor that is connected to ground. So this PMOS is always on, okay? And the logic itself is implemented by the corresponding pull-down network, okay? So the idea is when the pull-down network is active, the pull-up network is not off. Okay, that complementary action is not present here. When the pull-down network is active, pull-up network is also on. So what happens is there is a contention. There is necessarily a fight between PMOS trying to put a 1 and the pull-down network trying to put a 0. Okay, that's the idea of contention. And that's the idea of contention current during the pull-down network phase. And that is not present in CMOS logic, but it is present in other kinds of logic families, which hopefully we will get a chance to look at those today. One of those today, dynamic logic circuits. Okay, so contention current happens in logic families different from CMOS. Okay, in logic families other than CMOS, like pseudo NMOS logic, where the PMOS transistor or the pull-down network is always on. Okay, and when the pull-down network turns on for part of the cycle, what happens is there is a contention between the pull-up network and the pull-down network, trying to do opposite values on the capacitor. Okay, that's the idea of contention current. Contention current plus switching power consumption. Power contention plus power switching contributes to the dynamic. Okay, and then the power static is mostly the summation of all the different leakage currents. And the sum of the static and dynamic is the total power consumption. Okay, so we looked at some problems and then estimated the power consumption, the total static, the total switching power consumption for a for a system on chip SOC circuit. Okay, and then we talked about ways to minimize dynamic power reduction. There are a bunch of different ways, all these variables. I can switch the logic circuits less frequently, or I can reduce the capacitance, I can reduce the power supply, or I can reduce the operating frequency or the clock, the master clock. Okay, so these are all the different techniques to lower the power consumption that we looked at. Okay, and then we went into the idea of estimating activity factor. Okay, now there are techniques to reduce the power consumption. This is something that we did not look at, the clock gating technique. The idea is I'm going to provide clock only to those circuits, only to those registers that need to be on. Okay, what I'm doing here is the master clock here, in this case, this guy, is passed through a control gate. Okay, only if the output of this guy, only if this logic is 1, the clock value is going to be passed on to this. If this is 0, if the input value, the second input of the AND gate is 0, then the clock is not passed along to this register. This register right here does not see the clock changing up and down. So this register is not changing its output because there is no rising edge of the clock. So clock gating is a very interesting mechanism to cut off clock to parts of the circuit that don't need to operate. Okay, that's one mechanism to reduce the amount of capacitance that is switching on and off. Okay, so clock gating is one technique. So in the equation, alpha C VDD squared times F, that is the power switching. Okay, the other knob that I can use is to reduce the capacitance. Okay, we are already familiar with the mechanism of calculating the C diffusion. Okay, for example, when we were calculating the TPD rising or TPD falling, we were looking at the total capacitance to the left of a node and total capacitance towards the right of a node. Okay, so this is the parasitic cap and the load cap. Okay, so we looked at how to estimate the capacitance at a particular node by dividing it into the two constituent parameters, the parasitic component and the load component. Okay, so in addition to these in addition to these capacitances, which can be reduced by using fewer stages of logic and using small gate sizes. If I use smaller gate sizes, the capacitances are going to be smaller. In addition to that, what we want to do is we want to make sure we reduce the wire capacitance. Okay, so in other words, typically what happens is if I'm using so if you look at this, there is some capacitance coming from the parasitic component here. And there is some capacitance coming from the load component here. So those are the two capacitances that we have taken into account. The other capacitance that we have never thought about is the capacitance coming from this metal wire. Okay, metal wire. If a metal wire is running on top of another metal wire separated by some dielectric, what happens is when there are multiple layers of metal wires, if there is an underlying different layer of metal underneath that, what happens is there is a capacitance that is coming from this routing just by the fact that I'm making a long metal connection from one gate to another gate. that metal itself produces some capacitance. That's the idea of the wire capacitance. Okay, so we never talked about that. There are mechanisms to reduce the wire capacitance by using good floor planning and keeping communicating blocks close together. Okay, so there are techniques to reduce that as well. So it is enough for us to, from this side, it is enough for us to realize that there is a parasitic. So there is a parasitic capacitance. Or the self-loading, and there is the C load plus the C wire. There are more than these two components to the capacitance, okay? And we want to reduce the capacitance because by reducing the capacitance, I can reduce the power consumed, okay? That's the idea. Now, the other parameter, power switching, equals to alpha C VDD squared times F clock, the master clock. So the other parameters that you want to reduce are voltage and the frequency. Okay, voltage and frequency. And there are different techniques. One technique is to use voltage domains. Different parts of the chip use different voltages. If there is a part of this switch that needs a lower voltage, I operate it at a lower voltage. If there is a certain part of the chip that needs to respond very quickly, that needs high rate of operation, I operate that at higher voltage. So using different voltage domains is one technique to reduce the overall power supply and the overall power consumption, especially because power supply VDD has a quadratic effect on the power. Okay, so there are different techniques to reduce the overall power consumption. Okay, we will not talk about the static power example. It's mostly calculating the leakages, the different leakages that are coming from the MOSFETs. Okay, and another technique to lower the power consumption is to use what is known as power gating. Okay, the idea is to turn off power when a block is idle. If a particular block is idle, okay, what we do is I use a MOSFET transistor, a PMOS transistor. If I put a 1 on this sleep input, all the PMOS transistors are going to be off, okay, and then the VDD here is not going to pass through the power gated block below. Okay, so I'm using switches in between VDD and the power gated block so that I can turn off the power supply when a particular block is idle. Okay, so these are different techniques. Power gating, we looked at clock gating. Okay, we looked at different techniques to lower the power consumption. That's the discussion about power consumption that we did in the last class. Any questions so far, please? Okay. Now let's move on to a different topic, what is known as dynamic logic circuits. Okay, dynamic logic circuits. If you see the power